So anytime you have more than one reactant, you have to figure out which one of the reactants is going to run out first. In this question, it told us we had more than enough hydrogen. So meaning my nitrogen was going to run out first. If I have extra hydrogen, that means my nitrogen is going to run out first. So the example I like to give, and I even put it on the video that I posted online, but I just kind of want to summarize it because I don't want you guys to make it harder than what it is. I'd like to give a hot dog example. And let's say that if I go in my closet right now and I'm trying to figure out, oh, my kids are hungry, I want to make them some hot dogs really quickly. I got some leftover hot dogs from this weekend. And I say, oh, okay, I look in the freezer. I have about 4 hot dog wieners, and then I only have 2 hot dog buns. How many hot dogs can I make, guys? If I have 4 wieners in my freezer, but in my bread pantry in my cabinet, I only have 2 hot dog buns, how many hot dog buns can I make?
2.
4.
2, yeah, Jaleesa, I see you. So I can only make 2 hot dogs, 2 complete hot dogs at least, with the wiener and the bun. I can only make 2 complete hot dogs because I do not have enough wieners. I'm sorry, I do not have enough buns. So it's like, this is my equation. This happens a lot, meaning if this was my wieners and these are my buns, I can only make 2 hot dogs. And we all see that because I only have enough buns to make 2 hot dogs. So I'd say if I have 2 buns and more than enough wieners, that's what that is essentially saying. When I have more than one reactant, one of them's gonna be extra, the other one's gonna run out first. The one that runs out first, we call that the limiting reactant. It limits how much product I can make. These 2 hot dog buns limited how many hot dogs I can make in general. Does that make sense, guys?
Kind of.
Yeah. So in our example, the one you gave us with 3 hydrogen plus nitrogen equals what's that?
The 2 ammonias?
Yeah, the 2 ammonias.
Mhm.
So our limited thing in that problem telling us would be the nitrogen, right?
Exactly, yes. So the limiting reactant in this case, in this problem only, is the nitrogen, because it said I had more than enough hydrogen. So I had extra hydrogen, my nitrogen ran out first. So in reality, I could only make this much ammonia. So in tomorrow's lecture, I go over how you figure out how much product you can make if you have 2 reactants or more. You have to figure out which one's your limiting reactant. And the way you figure out which one's your limiting reactant is you simply set up these same stoichiometry problems. And when you set these stoichiometry problems up, you got to do one for, let's say, for instance, let's say it said I had 3.5 moles of nitrogen and 3.5 moles of hydrogen. I'd have to do a calculation then saying, I have 3.5 moles of hydrogen. How much ammonia can I make? The ratio is now 2 to 3, 2 ammonias for 3 hydrogens. So if I put that in my calculator, I know I'm going over it fast, guys. I just want it to be clear for tomorrow. I'm summarizing it. I would only have 2.3 moles of ammonia. So this is a totally different problem. Let's say it didn't say more than enough. Let's say it said I had 3.5 moles of hydrogen and 3.5 moles of nitrogen. I'd have to set up 2 calculations. Whichever one gave me the least amount of ammonia is my answer. So technically, this would be my answer. Just like with the hot dog situation, it's like I set up 2 calculations. the buns gave me the least amount of product, that's what my answer is, that least amount of product. And that's all tomorrow's class is talking about. And when we talk about limiting reactants, it's just kind of what it sounds like, limiting reactants. A limiting reactant is always a reactant. It's never going to be a product. It's always going to be on the left side of the arrow signs, and it literally will limit how much product we make. If I give an example right quickly, let's say I have 2 like this, plus oxygen gas forms magnesium oxide. You see I have more than one reactant. That means one of these reactants is going to run out before the other, and the one that runs out before the other one is called a limiting reactant. So I'd have to figure which one runs out first, and the way I figure out which one runs out first is I go through this whole scheme and figure out which one gives me the least amount of product. Okay, so I gave you guys a hot dog example on the video and before I left on Monday, which just said if I have 2 wieners and 4 hot dog buns, we all agreed that I could only make 2 hot dogs because my wieners limited how many hot dogs I could make. Same thing happens in chemical reactions. One of the reactants limits how much product you can make. So let's just do a quick example. And then I'll do an example from the worksheet, the limiting reactant worksheet, as well as the percent yield worksheet. So if we look at this example, it says when, let me let her in. When 10.1 grams of magnesium react with 10.5 grams of O2, how much magnesium oxide can be produced? Now, in this case, the way I solve these problems is you will always have 2 givens. So basically you have 2 numbers. I have 10.1 grams of magnesium. So I'd write this up top, 10.1 grams of magnesium. And I also have 10.5 grams of oxygen gas. So I have 2 givens, and anytime you have 2 givens, basically you got to figure out which one runs out first. Even though these numbers are similar, you would think, oh, 10.1 is less than 10.5, so it's going to run out first. But that's not necessarily the case. What ends up happening is 10.1 grams of magnesium is a different amount than 10.5 grams of oxygen because they have different molar masses. So they'll produce a different amount of magnesium oxide. So what we have to do is go through our steps and figure out which one's going to produce the least amount of B. And in this case, I'm saying for one calculation is A, for the other calculation, this is A, and for both calculations, this is B. So you guys following me so far?
Yes.
Okay. So if I set up 2 calculations, I'll just start off with the magnesium because that's the one I see first. In this case, I have 10.1 grams. Here. In this case, I have 10.1 grams of magnesium. And then I can say, here. And then I can say, okay, I'm just going to go through my steps that say if I start off with grams of A and I want to convert it to B, converting it to B actually means I can stop right here at moles of B. Most of the time we go to grams of B because there's another step after this where we sometimes have to calculate the percent yield. But actually to figure out which one gives the least amount of product, I can always stop at moles of B. But so in this case, I'm just gonna stop at moles of B because that's all it's trying to figure out, how much magnesium oxide I can make. And it doesn't specifically say how much in moles, so I'll say it says how much in moles does magnesium oxide. All right, so 10.1 grams of magnesium. The first step says if I start off with grams of A, I need to convert it to moles of A by simply dividing by the molar mass of A. I look at the periodic table. The molar mass of A, which is magnesium, is 24.31. All right, so that's the molar mass of A. Second step says, let's just do the mole to mole ratio because that's how I'm gonna get to B. I look at the balanced chemical equation and the ratio is what, guys?
1 to 2.
We're looking at B to A.
1.
Oh, 2 to 1, sorry.
2 to 2, 2 to 2.
It's just 1 to 1. Oh, yeah.
Or 1 to 1,
What is it?
whichever one you
Yeah.
want to say. I'm looking at magnesium versus magnesium oxide. So in this case, I'm saying 2 moles of magnesium oxide for every 2 moles of magnesium. If I put that in my calculator, 10.1, open parentheses, 1 divided by 24.31, and then times 1, basically, I end up getting, with 3 sig figs, 0.415. So I'll say this gives me 0.415 moles of magnesium oxide. Now I have to do a similar calculation, but instead of starting off with magnesium, I'm gonna start off with my other reactant, which is oxygen, and try to figure out, is it gonna give me less amount of magnesium oxide? So in this case, it says I had 10.5 grams of oxygen. So I'm gonna say 10.5 grams of oxygen. I'm gonna do the same thing, except I'm gonna use the molar mass of oxygen. What's the molar mass of oxygen gas, guys?
16.
32.
Okay. It's gonna be 32. Remember, this is O2, so 16 is just O, but I gotta say 16 times 2, which is 32.00 grams of O2. And now what's the ratio from magnesium oxide to oxygen?
2 to 1.
2 to 1, perfect. So 2 moles of MgO or 1 mole of just O2. And I put this in my calculator. And once again, I need 3 sig figs. And I end up getting 0.656 moles of magnesium oxide. So in this case, the least amount is going to be this 0.415 moles of magnesium oxide. So if the question asks how much magnesium oxide can be produced, this is how much can be produced. This is the least amount. I do not have enough magnesium to make this much. Just like with the wieners and the hot dog buns, clearly I have 4 hot dog buns and I could make more hot dogs if I had more wieners like this much, but I don't have enough of the other reactant to make that much, so I can only make this. We say this is how much can be produced. We say that the magnesium is the limiting reactant. So if the magnesium is the limiting reactant, what we call this number right here, we call that number the theoretical yield. And the theoretical yield is saying if everything went perfect in the lab while I was running this reaction, while I ran this reaction, magnesium plus oxygen to make magnesium oxide, if everything went perfect, I should be able to make this much magnesium oxide. So theoretically, I should be able to make that much. So the theoretical yield and how much can be produced are the same number. I'll say it's how much can be produced. It's not necessarily how much is produced. Does that make sense, guys?
Yes.
Yeah.
Okay. All right, so if we look at this limiting reactant worksheet, if we pull out this limiting reactant worksheet that I posted, and let's just pick one out, let's say, for instance, number 3. If we look at number 3 on this limiting reactant worksheet, that looks like this. Basically, I'm asking you similar questions that says, what's the mass of silver chloride? Or what mass of silver chloride is produced if you start off with 2 givens. So basically, you start off with a mass for both of your reactants, and you have to figure out how much silver chloride you can make. So let's pull this out. I have it here in case you don't have a printer. But let's try to work on this one together so it's clear what I'm asking you guys to do for 6 through 10. Now, in this case, the difference in the reaction that I just gave you for example, is magnesium plus oxygen gas giving magnesium oxide. There is only one product here. On the worksheet, a lot of these reactions have 2 products. So if it has more than one product, that's no big deal. In this case, it's specifically asking you about silver chloride. And since it's asking about silver chloride, that's the one product that we care about. So you just kind of have to read the question and figure out what you're looking for. The first thing we always have to do is make sure we have a balanced chemical equation. So I don't think any of these are balanced for you. You have to spend a second and balance these equations. So let's spend a second and try to balance this equation. Number 3, I'm looking at number 3. What do you guys see?
It looks balanced.
Yeah, it's already balanced. There's one of everything. Remember, there's one nitrate on both sides, so don't try to break those nitrates apart. So it's already balanced. It's like there's basically a 1 in front of each one of these substances. Now, when we go to answer the question, if I rewrite this up here, let's see, so I can make it a little bigger. This is silver nitrate plus sodium chloride reacts to form silver chloride plus sodium nitrate. It's already balanced. The question's now saying, okay, if I start off with 53.42 grams of silver nitrate, so that's 53.42 grams of the silver nitrate, and I mix it with 14.19 grams of the sodium chloride, question mark, how many grams? Because this one's asking for the mass. How many grams of silver chloride can I make? This is what number 3 is asking us. So once again, we'd have to recognize for one calculation, this is my A and this is my B. For the next calculation, this is my A and this is my B. So let's start both these setups so that way we can have some of these molar masses calculated. The first one All right, you guys, let's start it off together. If we start off with 53.42 grams of silver nitrate. So if I start off with 53.42 grams of silver nitrate, what's my first step?
By the molar mass.
The molar mass. I'm going to divide by the molar mass, so I can say 1 mole of silver nitrate is equal to, and I have to look on the periodic table, figure out what the molar mass of silver nitrate is.
I got 169.88.
169?
Yeah.
Okay, can I get someone to second that? Say it one more time for me, Malika.
169.88.
Okay, that actually sounds similar. All right, 169.88 grams of the silver nitrate. All right, so that's my first step. What's my second step, guys?
Mole
Find the
over.
ratio.
The
The
second
ratio.
The
is
ratio.
the mole to mole ratio. So remember, this is my first step. We're going to divide by the molar mass, and we're going to use the mole to mole ratio. What's the mole to mole ratio in this case?
1 to 1.
1 to 1.
1 to 1. So basically 1 silver chloride for 1 silver nitrate. And then the last step says, because I'm looking for grams of B, or grams of silver chloride, I need to then multiply everything by the molar mass of silver chloride. What do you guys get for the molar mass of silver chloride?
43.32.
43.32?
143.32.
143. Okay, sounds good to me. 143.32 grams of silver chloride, like this. All right, so I'd put this in my calculator. 53.42. And once again, how many sig figs do I need?
4.
4 sig figs, okay. Anybody have an answer yet?
45.07.
45.07, anybody can second that for me?
I
45.07.
second that, yeah.
All right, cool, 45.07, this is grams of silver chloride. All right, so that's one of my calculations.
I have a question. I'm still really confused as sometimes when we need to use like the B portion or the A portion, or if it's when we're converting from moles or molecules, like it's not clicking for me.
Okay, so if we just follow the scheme, so that you're saying which one's A and which one's B?
No, I get the A-B thing. I'm not getting, when do we use, like, how do we know, like, not to use the B formula or not to use the A? Like, when the question asks to find the molecules.
Okay, so that's just like saying, it's kind of, if you think, you got to think about them as two different things. You're saying on this worksheet when the question says find the molecules?
Yes.
Okay, so you know here in this last step, it says, let's find the grams. That's normally what we're looking for, finding the grams of B, right?
Right.
So if it's asking us to find the molecules of B instead of the grams of B, we know how to go from moles to molecules. Instead of saying this last step of multiplying by the molar mass, the last step would say 1 mole of B equals Avogadro's number. You get what I'm saying?
Yes.
You know what I'm
No,
saying?
I didn't want you to go there with that.
Yeah, I think you just confused me too.
Oh.
No, 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 no.
Okay, so these are just kind of these are just conversions. Remember, it's just like saying the whole point. You always got to do this step. You always have to do this step. This step gets you from substance A to substance B. Now, the last step can change because it's saying, what if I want to figure out how many molecules versus how many grams? So to figure out how many grams, if I'm going from moles to grams, moles back and forth to grams, we know to use the molar mass. But if I'm going from moles back and forth to molecules or any type of particle, I got to use Avogadro's number. So I'm just saying AV number. That's the only difference. It's like you'd cross out this last step. So you'd set everything else up the same way, except you'd use Avogadro's number for the last step versus the molar mass. It's simply just saying, once you get here, you're going to have your answer in moles and take that number that you get in moles and convert it to molecules.
Okay.
You get what I mean by saying it that way?
Yeah,
So-
sort of.
So it depends what the question is asking for. If it's
Yeah.
asking for molecules or atoms, or
Right. So like
that
if we,
will be the last step, right?
yeah, if we look at number six says, what does it say? Oh, number 6 says you're starting off with molecules. So it's not asking you for, it's still asking you to solve for grams in number 6. But it's not saying, it's saying you start off with grams of aluminum and then molecules of chlorine. So if you're starting off with grams of aluminum, you get how to go from grams to grams. But let's say you wanted to go from molecules to grams. The only difference in this step is that you would use Avogadro's number. You'd say 1 mole equals Avogadro's number.
Okay.
The whole point is,
So we're using Avogadro's number here as well?
no, this is,
Oh, okay.
let me finish this problem, Malika, then I'll come back to your question. So it's not too confusing.
Okay, sorry.
Yeah, I'll come back to it. So basically, let's go back to number 3. Sorry to get sidetracked. Let's go back to number 3. We did our first calculation. We got to do our second calculation. Our second calculation says we're starting off with 14.19 grams of sodium chloride. We essentially have to do the same thing, go through the steps. So we're going from grams of sodium chloride to grams of silver chloride. So the first step, we're gonna divide by the molar mass of sodium chloride. The molar mass, does anyone have that one?
58.45.
58.45. All right, what's the mole to mole ratio here?
1:1.
1 mole of silver chloride will give me 1 mole of sodium chloride. Or sodium chloride gives me 1 mole of silver. All right. And then the last step says we're then gonna do the molar mass of silver chloride, which we've already done. So all we're doing is copying this last step, which says 143.32 grams of silver chloride for 1 mole of silver chloride. All right, so let's put this in our calculator and see if we get the same number.
37.79.
37.79, anybody else get this?
I got a different,
I got 34.79.
I also got 34.
Yeah, I got the same.
Okay,
34.79.
all right, maybe just as a typo, Malika, 34.79 sounds fine. All right, either way, this is how much silver chloride we can make with this amount of silver chloride. Which one's our limiting reactant? Which one of the reactants is gonna limit how much we can make?
Sodium chloride.
Sodium chloride is our limiting reactant. So this right here is our limiting reactant. And then we say that this number right here is how much we can produce. This is all the silver chloride we can produce because we do not have enough sodium chloride to make this much silver chloride. Remember, we call this our theoretical yield at the end of the day. All right.
So basically the limiting reactant is the 14.19, correct?
Well, it's saying which reactant. You don't even have to say the number. It's just saying which reactant is going to limit how much you can make. Out of these two reactants, which one's going to limit the product? And it's going to be the sodium chloride.
Okay.
All right. Now, is this clear right before I go on? Because I want to quickly go on and cover percent yield. When we talk about questions like number 6, if it's asking you about molecules, if you're starting off with molecules, okay, let's just do a quick refresher, guys. Remember when we talked about the mole concept, we had that whole worksheet that said, if you want to go from grams to moles, you got to use the molar mass. MM stands for the molar mass. If you want to go from particles to moles, you have to use Avogadro's number. And then if you want to go from liters to moles, you have to use the molar volume. All right, Avogadro's number said 1 mole equals 6.022 E23. This one said 1 mole equals 22.4 liters. This one says 1 mole just equals the mass from the periodic table. You guys remember this?
Yes.
So the only thing that we're doing is we're taking these conversions that we learned and plugging it into our same scheme right here. But typically, when we're doing these types of calculations, we're using grams. So the first step is going to be use the molar mass because we're trying to go from grams to moles. If we started off using particles, the first step would be to use Avogadro's number. 1 mole equals Avogadro's number because we're going from particles to moles. If we started off with liters, the first step would say 1 mole divided by 22.4 liters, because the whole thing is to get to moles first. And these are the different conversions that we've learned to get to moles. Does that make more sense?
I think so.
Okay, so I'm not trying to confuse you with the molecules here. Same thing with the last step. If the question's saying how many liters can I produce, you'd have to then multiply by the molar volume. If it said how many molecules or how many particles I can produce, you have to multiply by Avogadro's number. And since usually we're trying to figure out how many grams, because in reality, we are measuring the grams on a balance because that's the type of instrument we'd have in the lab, we're going to use the molar mass. So these steps can change out with any of these conversions. It's just the problems you're going to see most likely are going to be from grams of A to grams of B.